So for question 3, the synthesis of ethyl chloride is accomplished by reacting ethylene with hydrogen chloride in the presence of an aluminium chloride catalyst. So this is your reaction. The process data and a simplified schematic flow chart are given below. This is your schematic flow chart with its data. So we'll put all the data in to a new flowchart that we will create later on. So the feed A contains 100% of HCl at 0 degrees Celsius. Reactor operates in an adiabatic system with an outlet temperature of 50 degrees Celsius. Feed B contains 93 mole percent of C2H4, 7% of C2H6 at 0 degrees Celsius. Product C here contains 1.5% of the HCl. Okay, so take note that this is percent, not mole percent, so it means 1.5% of the HCl in feed A and 1.5% of C2H4 in feed B. Okay, and all of the C2H6 that enter the reactor. Product D contains our desired product, which is C2H5Cl in the liquid phase at 0 degrees Celsius, and recycled to reactor is the ethyl chloride as well at 0 degrees Celsius. Okay. And you are given this, the vaporization enthalpy. So the reaction is exothermic, and if the heat of reaction is not removed, heat of vaporization. So if the heat of reaction is not removed in some way, the reactor temperature could increase to an undesirably high level. To avoid this occurrence, the reaction is carried out with the catalyst suspended in liquid ethyl chloride. As the reaction proceeds, most of the heat liberated goes to vaporize liquid, making it possible to keep the reaction temperature at or below 50 degrees Celsius. The stream leaving the reactor contains ethyl chloride formed by reaction and that vaporize in the reactor. Okay, so this stream passes through a heat exchanger where it is cooled to 0 degrees Celsius, condensing essentially all of the ethyl chloride and leaving only unreacted C2H4, HCl, and C2H6 in the gas phase. A portion of the liquid condensate is recycled to the reactor at a rate equal to the rate at which ethyl chloride is vaporized, and the rest is taken off as product. At the process conditions, heats of mixing and the influence of pressure on enthalpy may be neglected. So A, at what rates do the two feed streams enter the process? So this we need to calculate for feed A and feed B. Calculate the composition in mole fractions and molar flow rate of product stream C. So we need to find their mole fractions and the molar flow rate in the product stream C, and C, write an energy balance around the reactor and use it to determine the rate at which ethyl chloride must be recycled. So this is a diagram that we redraw again, and we put in all the information in. We label it with A, B, C, and D stream along with its number of moles, inlet stream names N1, N2, N3, N4, and so forth. Okay. So for part A, we will first convert the stream D into moles. Okay, so we were given 16,000 kg. In the question, it was written 1,600, so that was a mistake. Please take note. And after converting D to moles, we get 24,800 moles of ethyl chloride. So based on the specification given from the question, so N3, which is from stream C, is 15% of N1, okay? And N4 is 15% of C2H4, which is 93% of the total stream in B stream. This is equation 2. So N5 is 7% of N2, equation 3. So we'll start off with elemental balance using Cl. So N1 in equals to out. This is your in, this is your outlet. So N1 equals to N3 plus 2 for 24,800. So this is your equation 4. Substitute equation 1 here into equation 4 and solve for N1. And then we can also solve for N3, which is this. We will then do overall C balance. Okay, so your inlet equals your outlet here. So your inlet contains C2H4 in the B stream and C2H6 in the B stream. Okay, and your outlet contains C2H4, C2H6, and C2H5Cl in your C and D stream. Simplify your equation to get equation 5 as so, and then we can substitute equation 2 and equation 3 that contains N2 over here to equation 5 and solve for N2. Okay, with N2 and N1 being solved, we can solve for N4 and N5. We have already solved for N3. So N3 here, solve, N4 and N5. So to calculate for the mole fraction in stream C, we basically take the total number of moles in the product stream C, okay, and for each species divide by its total, multiply by 100%. Okay, so for part C, write an energy balance around the reactor and use it to determine the rate at which ethyl chloride must be recycled. So our reactor operates in an adiabatic condition, and taking the reference for this at 0 degrees Celsius. So for C2H4, the enthalpy is the latent heat, which we integrated from 50 to 0 degrees Celsius. So from table B.2, we look for our A, B, C, and D. Okay, I'm sure you're familiar. And we found this 2.18. Okay, we do the same for C2H6 HCl, and these two, one at the liquid phase and one at the gaseous phase. So for the liquid phase, the H is the reverse of the vaporization. Okay, makes sense? And that is negative 24.7. Okay, this was already given in the data in the question. Okay, substitute all your enthalpy values for each species into the inlet and outlet enthalpy table as so. Okay, so for the adiabatic reactor with negligible kinetic energy, potential energy, and shaft work, we get delta H is equal to Q, which equals to 0. So using the heat of reaction approach, delta H is equals to 0, so N out minus N in divided by V multiplied by the heat of reaction at 0 degrees Celsius plus the sum of the enthalpy. So this is the specific enthalpy multiplied by the number of moles or your flow rate will give you your enthalpy in the outlet and your sum of your enthalpy in the inlet. Okay, so in this end out here, we will use HCl to get the extent of reaction E here. Okay, so we have already determined this in the outlet and the inlet, multiply by HR, okay, plus the outlet here, outlet stream, we have C2H4, C2H6, HCl. 1, 2, 3, 4. Oh, and ethyl chloride. Okay, and then you have your inlet stream. Okay, so this leaves us with 8.07. Okay, so N6 is 8.07 times 10 to the power 4 moles of C2H5 chloride in the reactor effluent. So C2H5Cl that is recycled is this minus this value, which is your product, your D stream. Okay, your D stream here. This is your recycled one. Okay, and then we get 5.59 times 10 to the power 4 moles of ethyl chloride that is recycled back into the reactor.